Here we go. Good morning, good afternoon, good evening, YouTube. Listen, I hope this really helps you out as much as it's helping me out. Creating these self note videos for myself prior to the exam, and depending on how it all goes, I might just continue this to continue and help people that just want to know the direct concept right away how to solve PE exams. This section or this video is for per unit systems. One of the things that we will probably most likely see on the Power PE exam. So I'm just going to go over this to remind myself. I think these videos are very helpful in the end because there's times where we do a lot of driving, and rather than listen to music, I would rather listen to this and just to kind of capture all the key points that I really need for the exam. So what you see here on the screen to the left is the formula that is actually in the reference book. So this is given to you prior to the exam or during the exam. And the one on to the right is also converting the new to old, or sorry, from old to new. So what I wanted to show you here, the per unit system in the reference book gives you examples of how to solve for the base current and the base impedance for a single phase versus a three phase. And then that one, whereas you could see, is just a conversion. One thing really to be mindful, this equation for some reason my mind is just doesn't register it as much. So what I like to do is really just kind of break it down to realizing that this is, in the end of the day, it's just solving for the impedance. So really, if you take a look at, it's Z equals V squared over S. That's really what it is. And I think the best way to look at it is this is the old, and this is the apparent power that's old. And the way this actually comes out to be, if you really separate them, meaning if you combine the voltages together, the whole point is really to cancel out the units so that you can actually get the per unit, right? So the Z old is usually given to you in reference to a percentage or a decimal. So if you take a look, all it is really, so here's your Z new, Z old, and all you have to do is really just separate. So what I'm going to do for now, I'm just going to put V old here, and you could see that this is really the same thing, and then S old here. Okay, to cancel out the units, if the V old is at the top, then the V new is going to be at the bottom. Same thing with this. I know it says sold, but if S old is at the bottom, then the new is going to be here. And that's really how they derived this all together. But I really want you to kind of keep in mind with the following reactance values. This is very important because I'm sure we will run into this in depending on the question. So you got a steady state reactance considered as X or XD. Then you got the transient reactance X prime, and then you got the subtransient reactance. This is going to be your best friend when it comes to solving for the fault current. And the reason for that is because this is the least amount of resistance or reactance, which means it's the highest fault current. This is where the initial of when the beginning of the initial fault, this is where that subtransient reactance comes in. So in order to capture the highest fault current, this is what you would use. So be mindful if you ever run into a question where it lists all of those, you want to be careful and just follow and just stick with the X double prime. I'm not sure how would you call that, but you get the idea. Subtransient reactance is your best friend. Okay. Followed down here, let's just go ahead and look at some examples. So in this case right here, we have a transformer has a per unit impedance of 0.08 on a 25 MVA 69 kV base. What is the actual impedance in ohms? So one thing that we need to really keep in mind is the basic formula for a per unit is you have a per unit value over the actual value. So per unit equals actual over base. And that really works out for Z, I, or voltage. So in our case, we're dealing with a Z actual. So what you do is Z per unit equals Z actual over Z base. And to solve for that formula, then for Z actual, it would be Z per unit times the Z base. So in this example, you can see here, you were given the apparent power as a base and the voltage as a base, and they would like to know what is the actual impedance in ohms. So all you have to do is first you need to solve for the impedance base, and here's the formula, V squared over S. Just be mindful here, as you can see, they did only 69 square over 25 because they're really following this word by word. So you could see here, for example, K V line to neutral versus, here's the KV line to line over MVA. So they're using the units in the thousands and then to the 6th power. My advice would be is really to just spell this out completely. So just put at 69 times 10 to the 3rd over 25 times 10 to the 6th. And it's going to come out the same way. And you should be able to get 190.44. Once you get the base value, because they asked for the actual impedance, then you take that actual, multiply it by the per unit value, and your answer is 15.24 amps, ohms. All right, here's another good example here that I would really like to kind of make sure that you guys understand the concept. This is for a fault current. So once again, remember what I mentioned, that for a fault current, your best friend is going to be that subtransient, which is considered as, I'm going to call it X double prime. Let me know in the comments if that's the correct terminology or not. But anyways, this is your subtransient. Okay. Got to work on my handwriting. Let's see here. A generator has a subtransient reactance. So in this case, they actually did give it to you. Be mindful on the exam. You might run into, without writing the word subtransient, they might just say XD or X double prime, or they might throw you off and by giving you the steady state and the transient and the subtransient as well, just to kind of throw you off. So a generator has a subtransient reactance of a 0.15 per unit on a 100 MVA, 13.8 kV base, and it's a three-phase fault current occurs at the terminal. Determine the fault current in amperage. Okay, so there's two methods to solve for this fault current, but what we'll do here is focus on the per unit, and then I'll show you the other method, which is they call it the MVA method. So in this case, what they did is you were given, I like to kind of list out my variables. So where's my S base? My S base is 100 MVA. My voltage base, and this is line to line, meaning three-phase, 13.8 kV. So here, what I would like to do, because they're asking for the current, I would have to solve for I. So given it's a three-phase, be mindful that your apparent power equals square root of 3 V line times I line. So to solve for I line, we're looking at the apparent power over square root of 3 times V line. So in this case, let's go ahead and plug it in. You got 100 times 10 to the 6 divided by square root of 3 times 13.8 times 10 to the 3rd. And if you do that, you get an I base, as you can see here, 4185.7 amps. So that's your I base. Now what you need to do is really you want to convert or solve for the per unit in order for you to solve for the actual I fault. One thing you want to keep in mind here, they're giving you the subtransient reactance. So this is a per unit for Z, right? So best way to look at it is if you take a look at this equation right here, the way that this is actually broken down, think of it as Ohm's law, right? So what is Ohm's law? You have V equals IR or we could say V equals IZ. So if you want to solve for this reactance or impedance, Z would equal V over I. So for given questions like this, most likely it's safe to assume that your voltage in terms of per units, it is actually known as 1, right? So once again, okay, sorry about that. What I wanted to do here is really solve for I. So I equals V over Z, right? So this is the one that we're really looking for. So now converting all of this in terms of a per unit, I per unit equals V per unit over Z per unit. We did assume that, and it's safe to assume that the V, under the assumption that V per unit is equals 1, then this equation comes out to be 1 over Z. Hence, if you take a look at here, your I per unit comes out to be 1 over subtransient reactance, and that would give you the I per unit. So let's go ahead and just solve for it. 0.15. So your I per unit is 6.67 PU. Now you got the idea. To solve for the actual I, you got the I base and you have the I per unit. You know for a fact that the equation is per unit equals actual over base. In this case, we want the actual, so I actual equals I per unit times I base. And you just plug in the numbers. So just be mindful of that right here, that when given the subtransient for an I fault, it's 1 over x double prime. Okay? Another way to solve for this, let's just go ahead and just erase everything on our end here. Okay. Is using the MVA method. And the way to use the MVA method is basically, all it is that you take the apparent power divided by the subtransient reactance, and that will give you the system total apparent power at fault. So right where the fault is, you're going to get that total fault apparent power. All you have to do here, the MVA method, all you do is, let's just write this down. S is given 100 MVA, and our reactance, subtransient reactance, is 0.15. The MVA method, all you have to do is you would say S equals 100 MVA, and this is going to be the at fault, over 0.15. And let's see what you get here. So 100 e to the 6 divided by 0.15. You get a large number, so let's just take a look. Okay, so according to this, the apparent power at where the fault is, this is equals to 666.67 MVA. You take that and then you actually solve based on the given voltage. So now you know for a fact to solve for the actual current, you know that for a three-phase, S equals square root of 3 V line times I line. So to solve for I line, you would use the SF S over square root of 3 times the V line. So if you actually plug this in, you should get the same answer as the one right here, 27,000. So let's go ahead and try it out. Divide this by square root of 3 times 13.8 e to the third and I got 27,917, roughly somewhere in that area. All right, so now you know the methods as a per unit and then the MVA. I personally like to use the MVA if this is all given, but in case that they ever ask you for the actual per unit value, then you're going to have to use the per unit system. I hope this actually helped out. If not, moving on to the next video.